try and kind of keep it very, very basic. It's basically a microphone. Okay. Okay, so the title of the talk is double-scale SYK and basically code diagram, the code diagram technique for solving this model. And I want to talk about space-time aspects and some random matrix theory aspects. So I'll remind you the rules. I'm going to work with a slightly different normalization, but that's just some technicality. So I have n Majorana Fermi, right? Please don't trust any factor of 2 or I or anything. So I goes from 1 to n. And the index set I is a list of p numbers out of this. Okay, and they basically characterize a monomial of the psi I. So psi capital I is psi I1 up to psi IP. And this is each of the monomials that show up in the SYK interaction. And I sum over all of them with random coefficients. So the Ji are Gaussian variables that satisfy this condition. This is going to be my normalization. It's slightly different than the usual one, but okay, morally it's the same. So double scale, of course, if there are any questions, feel free to stop me at any time. And I'll only try and be briefer than an hour and a half. Okay, so the double scaling limit is the following. We take n to infinity. We also take p to infinity, such that p squared over n is fixed. And I'm going to call this lambda. And the parameter, which I will actually use most of the time, is e to the minus lambda. You've seen this in Ahmed's talk. And I should also add one notation that whenever I have these kinds of brackets with a subscript j, this means that I'm doing an ensemble average over these couplings. Okay. Good. So now what wants to evaluate is a trace e to the minus beta h average over the couplings, and you can write this in two ways. One is you just do an expansion, and then you go and evaluate each of these polynomials. Okay. Or you can do this a little bit better. Which is, I'm going to write this as trace of 1 minus beta h over L to the Lth power, and take L to infinity. I mean, one way or another, I'm going to have to evaluate some expectation value of h to some power. But this is a little bit more space-time-ish, basically, like I see really the evolution. Okay, so the way this is evaluated, if you remember from Ahmed's talk, is using chord diagrams. So suppose I give you this kind of a monomial, then you draw a circle, and you pair the points. Something like this. This is a chord diagram. And then trace, in the normalization that I just had, trace h to the k is 2 to the n, and then a sum over all the chord diagrams, which I denote by CD, q to the number of intersections. So this is a statement that is true in the large n limit in the double scaling. If you want to evaluate this in a kind of the simplest way to do it is to kind of cut this open somewhere and go say clockwise, and then at each point you can either start a chord or you can end the chord. So you're going to have something like this. This would be an example of a chord diagram. This is encoded in the transfer matrix. Which is the following. I start with 0 chords. I end here with 0 chords because all chords have to start and end somewhere. And in between, I propagate this with the rule that I can either start the chord without any penalty, and coming down, I might be intersecting some chords, so there's going to be some weight that's associated with Q. And you define the following transfer matrix. With zeros on the diagonal, ones below the diagonal, which correspond to two opening chords, and then when you close, there is this way. And this goes all the way to infinity. And the expression is that, let's call this MK. And I'm also not going to worry about this 2 to the n. You can insert it yourself in the relevant places. So MK is you start with 0. You do K processes in K points in which you either start or end the chord, and you end with 0. And if you want to make this a little bit more into a Hamiltonian, you can do the following. So I can conjugate this into a symmetric matrix. And I can basically conjugate by a diagonal matrix and bring T to this form. So now this is an Hermitian operator. Okay, and of course you can also write it this way. Okay. So now the main point of this construction is that I had something which was h to the k, and I turned it into t hat to the k. So there's a mapping between the Hilbert space of the theory after I average to some new Hilbert space, some auxiliary Hilbert space made out of chords, and a new Hamiltonian that's acting on it. And basically, if you believe me that you can expand and resum exponentials, which you can because the spectrum is well behaved enough, then any time that you have an evolution operator H in the microscopic theory and you do the ensemble averages, you are going to end up being able to replace this by e to the minus it hat t. Okay? And this is basically the ADS-CFT correspondence in the case of two-dimensional SYK versus two-dimensional space, because this is the microscopic theory, and then I do some averaging, and then I have some new Hamiltonian acting on some auxiliary Hilbert space, And this describes the bulk. And the way to see that describes the bulk is what Ahmed showed you, that if you go to the infrared of this transfer matrix, which is a rather easy thing to do, you basically get Liouville, which is, if you wish, a gauge fixed version of the Schwarzian. So you have this black box, you crank the handle, you do some combinatorics, and out comes the bulk. Of course, I'm cheating a little bit because the only thing that I get is the Schwarzian, but really, if you're looking at low energies, then the Schwarzian is the only thing that you have because ADS2 is rigid, and you just have the motion of the boundary particle encoded by the Schwarzian. But actually, the purpose of this talk is to, if I get to it, is to show you that you actually see the bulk explicitly. Like it's not just the boundary dynamics. You kind of get it on the nose or in your face, depending whether you like or don't like this proceed.
Sorry, I missed the beginning, but did you explain what operator takes you from H to T? I assume that T is Hermitian too?
This is,
So,
these
one
objects.
line higher up.
This one?
No, in between those things.
This one?
Yeah. Is there some U? Is there some operator U that?
It's not an operator. This is the effective dynamics after you do the ensemble average here. So if you want to compute trace of any object that has e to the minus IHT, this is a field theory. This is a field theory statement. So this is trace on the Hilbert space of the microscopic theory. Okay, now I take the ensemble average. Okay, so this is now a trace. This is now starting and ending with 0. Some stuff that I can tell you exactly how to map things here. And then there's e to the minus I t hat t. So this acts in the space of chord, in the Hilbert space of chords, which I'll define in a minute. But roughly, you can have, well, okay, I'll define that exactly. That's going to be the gravitational Hilbert space. And this is the field theory. So it's not that there's a one-to-one map from the Hilbert space of the field theory to the Hilbert space of gravity, but it's an effective description, and this H is replaced by T hat.
So T hat obeys width of the width? Does it annihilate states?
I'm going to get to that in a minute. In ADS2, it's a bit subtle as to what is. I mean, but this is H of this T hat is the generalization of the Schwarzian. Okay. So it's the boundary dynamics that's left after. Yeah, what I want to show is that it's really, you actually see the bulk, like in this description.
Does this replacement work even if you're calculating expectation values of double trace operators?
I'll get to double trace a little bit. I mean, it works, but in double trace there are some new features which I would want to highlight, but it works. Yeah, I mean, it's a very similar technique. Okay, good. Yes.
The matrix elements 1 minus q squared should be with squared.
Yeah, this should be with this. Thank you. You see, this matrix becomes is very simple, right? Because Q, when they go down, because when Q goes to Q is smaller than 1, then when you go down, it just has one diagonal and one diagonal below, one diagonal above and one below the main diagonal. That's why this thing went over to a d phi squared, if you remember in Ahmed's Ahmed did the reduction to Louville, right? Okay. Okay, so in particular, if I want to, okay, so basically the spectrum of eigenvalues of H is the same as the spectrum of eigenvalues of T hat. And this is a simple enough matrix analyzed by our friend the mathematician, and we know everything about this spectrum.
The other side of H.
I want to compute this guy. Okay. The spectrum of T, the spectrum that you get in the large and limit has a certain support and a certain density, and that's the same as what you would get from T hat up to one factor, which I want to highlight. So this guy, there's a 2 to the n just from the dimension of the Hilbert space, and then dE, mu of E, which is the density of eigenvalues of this matrix. And then I have these form factors, so there's going to be 0 E squared, and then e to the minus beta E. So this thing is rho of E of SYK. This is a simple factor. It's very easy to figure it out. It's basically determined by the asymptotia of this matrix. And this is some form factor that we know exactly how to evaluate. So this is the solution of the model, basically. The way that this rho looks like, it has different regions. So if you are around 0, this is just a Gaussian. Okay, so this is for Q, which is close to 1. And this goes in my conventions in this range. Okay. So this is when Q goes to 1, when Q is close to 1. So, okay, so where would the Schwarzian region be? Suppose I want to, right, this is not the spectrum that you get from the Schwarzian theory, right? So where is the, but I told you that this guy, actually in the limit, when I go to the infrared, and I also need to take Q going to 1 here, I should have said, goes over to the Louville action, which is a gauge fixed Schwarzian. So where is that in this energy range? What? Right. So I basically need to go to low energy if I want to get the Schwarzian. So this is the sinh. This is supposed to be a sinh of the square root of E. So this is the case where Q is about 1. When Q goes to 0, this goes over to the Wigner semicircle. Okay? So this thing extrapolates between ordinary random matrix theory, like beta ensembles, and something like SYK. And you can expect this, right? Because Q was e to the minus lambda, and lambda was p squared over n. So when Q goes to 0, that means that lambda is very large. So these are very long monomials, and you have many degrees of freedom. You're starting to fill up a lot of this 2 to the n over 2 by 2 to the n over 2 matrix.
Sorry.
Okay.
For Q equal to 0, you get a flat distribution.
For Q equals to 0, just a second. Okay, let me. You're a fan of beta ensemble, so I will dedicate the Q equals 0 discussion to you. So what does Q equals 0 mean? It means basically that when I have two lines that intersect, I look at all the pairings, and when I have two lines that intersect, I give it weight 0. Okay, so that means that when I compute trace h to the k expectation value, I only sum over non-intersecting lines. Okay? And then with weights 1. So I'm just counting non-intersecting lines, and that's exactly the moments of the Gaussian ensemble. Okay, just the two standard large N expansion, the planar expansion. Okay. So you can of course extract this from the matrix, but this matrix just implements this rule of non-intersecting guys. Okay. Okay. So so this thing is okay. So what are the main points that I want to make is that we can solve for all energy scales, right? Because we have an exact expression from the lowest energy to the highest energy, okay? In particular, this region, for example, has beta equals 0, so it's infinite temperature. I can do the infinite temperature phase of this model. But the thing that I want to spend a little bit more time on is the time scale that this thing captures.
Sorry, the analytic form of this is known, you said?
Yeah.
You know the exact.
You know everything here. Yes.
Is there a Heidegger behavior somewhere?
No. Look, I mean, there are I mean, like at this point you have to choose. Like you could say, okay, this is not gravity, and I'm not interested in it. It's something else, non-universal, blah blah blah. Not interested in it. Or you can say, which is what I'm going to say, because you know I think that's the correct thing. That whatever you deduce from this may or may not be exact as gravity that we know, say, in 4 dimensions, but this is a model which is a controllable full UV completion of the bulk, and you might as well try and study it and see what it gives you. Maybe it will teach you something that, even if it's not exactly gravity, you can then figure out, you know, say something about what is real gravity. Okay, so I want to talk about the time scales that are associated with this construction. And I want to keep in mind this distinction that I raised between this and ordinary RMT. Right, so in ordinary RMT, when I say ordinary RMT, I mean something of the form, some integral over the Hermitian matrices, and then e to the minus something which is the dimension of the Hilbert space, which I will call e to the s, trace v of h, where this is some potential. Okay? So I can think about v of h as h squared plus some gk h to the k. This is what one usually does. And then what happens is the way that you're going to describe this in perturbation theory is you know, you start doing a perturbative expansion in these G's, and then you hope to resum it. So the leading thing is, if I have a bunch of H's on a circle, the leading thing is that I just pair the H's, you know, something like this. And then suppose I bring down a G3H cubed, then there's a vertex that looks like this. Okay, and then maybe there's another one like this. But all the lines are non-intersecting, and I have these vertices. Okay, this is the Tooft double line notation. Now, what I want to argue is that our model is fundamentally different, because I am allowed to have non-intersecting lines, and that's actually the thing that gives the dynamics. You can try and force these objects into vertices, but that kind of misses the point. Like, you can always say, you know, something like this is a 4-vertex. But obviously here there's a single Q, whereas here you would need to tune an infinite number of vertices. So I want to think about this as a different universality class, which gives you 2-dimensional surface in a way which is not the toothed double line notation. Okay, and the way that the place where you would really see different physics is in certain correlators. Yes? Someone ask a question? Okay. Okay, so where would we see a difference? I mean, of course, you know, if you do substitutions like this, you can cook anything. It just becomes more and more complicated. And the place that you see the differences is, for example, if you look at the spectral form factor between random matrix, ordinary random matrix theory and this Q processes. Okay. Is, for example, if you compute the spectral form factor. Okay. So in ordinary random matrix theory, what would this look like? I assume some people have studied these models. Students, wake up.
Are there any students left?
Are there any live students? Okay. It's not an orchestra. Like, you don't do stuff like this and noises emerge. Like,
oh, okay, so it goes down and then it goes up and it sticks in the middle.
okay, so actually in random matrix theory it kind of goes like this. And this is, let's be more precise, I'm going to look at the connected piece. So I'm going to subtract the silly bit. And I'm going to take all of this and normalize it by this piece. Okay, so here there's another ZZ. In this case, this is 2 to the minus.
What is J?
J means I'm doing an ensemble average over the J's. Okay.
What is the horizontal axis there?
The size of the, okay, let me write this a little bit. So this is denoted as the connected piece, and it's basically this guy divided by Z beta plus IT, Z beta minus IT, again, I'm sorry, JJ, okay. So I subtracted the trivial piece.
You probably want to put that it's a function of t, so it won't ask you what is the x-axis.
So this is beta and this is t, okay. And what I am plotting is this connected two-trace correlator as a function of t, okay? And this roughly, I mean, morally speaking, it goes like this. There are some features here, depending on the ensemble, etc., etc. But this is 1 over the dimension of the Hilbert space, S squared. Okay. So this is what I'm going to get for this guy. If I go and compute it, but of course, if you write any, if you go and ask your condensed matter friend or StatMech friend to actually take a physical system and run simulations, you are not going to get there. What you're going to get is really some very large contributions and then it goes over to this behavior. This is called the ramp, and this is called the plateau. Okay, and these are typically much larger. So this is kind of the statement that only at very long times or very close energy separation, then you go over to RMT universality.
So this is an SYK.
Yeah, in SYK this is going to be the same thing. Right, and if this is in my normalization 1 over 2 to the n, then in this normalization in the double scaling limit, this is 1 over square root of n and then some function of lambda, which is a little bit less relevant for us. So this is a contribution which is much, much larger, and you can evaluate it using these double scaling techniques. Now, again, you could say different things about this. You could say, you know, gravity is only the infrared of SYK, and therefore I'm interested only at very long time. Okay, something important is that in SYK, this thing is again of order e to the s. Okay, so all of these guys are very, very long time, and for example, if you want to discuss something like Hawking radiation or anything at the page time or anything of that sort, you are really in this regime. And then there are much larger multi-trace correlators. Now what is multi-trace correlators? Multi-trace correlators is exactly two, you know, and some gravitational configuration with two boundaries talking to each other. So on top of the usual wormholes that you have, there are gravitational effects of two boundaries talking to each other, which are much, much larger than what you would get, you know, the 1 over 2 to the n effects, or there's, you know, gravitational wormholes, or all of this stuff. It's really, these models are fluctuating much more widely, and there's, well, okay, I mean, like connections between universes, which are much worse than you would have thought, much larger. So this is really a physical difference between these kinds of models and RMT models. All of this business of topological recursion relations don't really work for SYK. But of course you could say, okay, I'm just interested in very long times where this effect decays and this becomes important, and then you can use them. Okay, so for example, if you're interested, you can get some exact formulas, which is, for example, that the connected 2-point of the energies is this n choose p to the minus 1. This is really my small parameter. This is the thing that goes like e to the minus square root of n, and then d E1, E1 rho of E1, d E2, E2 rho of E2. Okay, so this formula has some physics in it, and so basically, what does, you know, what does this thing, okay, let me write this in a suggestive way, and then ask some of the students to throw in some interpretation of this. So I'm going to write this as d alpha e to the minus n choose p minus, no, alpha squared rho of alpha E1 rho of alpha E2. Okay. And then I'm taking the leading connected piece out of this. Okay. So what would be an interpretation of something like this? Okay, so this, of course, because this is a large coefficient, I'm sorry, this should be alpha minus 1 squared. So because this is a large number, this localizes close to alpha equals 1. So that would just give me rho E1, rho E2. That's the part that I throw out because that's the disconnected piece. And then there are corrections to this. Okay. And you see that this thing, what it does, okay, so what would be, how would you interpret a formula like this? Okay, and remember that the spectrum looks something like this. And there's a mode that dilates the spectrum with some measure. Okay, so what basically that means is that this whole spectrum is fluctuating a lot. Right, so all of this guy dilates and shrink a lot, much more than in ordinary random matrix theory. In random matrix theory, the tip is very, very rigid. It doesn't fluctuate much, and that's why the topological recursion relations work. Here you have very, very wide fluctuations of this spectrum from realization to realization. Okay, so these are, if you wish, some kind of global modes that live on your space and tell you that distinct universes are correlated with each other much more. And again, you could say, this is clearly a non-gravitational effect. I'm not interested in it. Or you could say, let's see what we can make out of it. Okay, so this is, and generally this technique of moments, which is the expansion that I had, basically works in this range. I mean, this is where it picks up, that's where the physics is captured by moment expansion. Okay, so I want to go back to the space-time and kind of substantiate a little bit more this story that the chord diagrams build up ADS2. Okay, so I'm going to start with the picture. Okay, so again, let's write the spectrum. And I want to be kind of close to space-time, but still study deviations from ordinary JT gravity, for example. Yes?
Just about the thing you just erased. So if the spectrum fluctuates,
Mm-hmm.
the fluctuations depend on Q, right? On the scaling parameter.
Yes.
Okay, so we say it fluctuates more, that Q goes to 0, Q goes to 1.
The Q goes to 1. Q goes to 0 goes over to the semicircle, and then you restore the rigidity. But it's always still much, much larger, right? It's going to be, the point is that, you're still working with finite lambda, but this becomes large, right? Because you have QE to the minus lambda. So the length of each of these monomials is still square root of n times a large number. So you're still not filling up the 2 to the n over 2 by 2 to the n over 2 matrix. So it's always sparse, but the level of sparseness decreases, and therefore you approach, for suitable observables, the RMT correlators, including the rigidity of the edge. Okay, good. So I want to be in a kind of gravitational regime, so I'm going to take Q to 1, but some finite, very small distance from 1, and I'm going to focus on low energy. So I'm going to have e to the minus beta h, and Q goes to 1, and beta goes to infinity. Okay, well, very large. Okay, I didn't tell you exactly how I scale things, but morally speaking, that's what I'm doing. So, and then let's draw a chord diagram. Okay, so this is in this picture where I have e to the minus beta h over L to the nth power. Okay, so each insertion here, there are L insertions, and each insertion is of something like this. So there's either an H there or not. Okay? Okay, and then I draw chord diagrams. Fine. Now what happens to this picture when Q goes to 1 and beta goes to infinity? So let's start with beta going to infinity. What happens to an expression like this in terms of this chord diagram when beta goes to infinity? Right, so I think about this maybe as an expansion. And I'm taking beta to be very, very large. Okay. How many points do I need to include when I take beta to be large? Okay, so I'm going to have more and more points. Right, just because when beta is large, I need to take more and more of this expansion. You know, it's dominated by some higher and higher term. So the number of points here goes to infinity, becomes very large. I'm not really taking to infinity, but it's some scaling of how it, and then a line, you know, can go further in because, you know, I meet, you know, when a line, say, goes from here to here, there are many intersections, but the strength of the intersection goes to 1. Okay, so there's no suppression. The suppression becomes smaller and smaller. So what I'm going to have is a picture where I have many chords like this. And what I claim is that in this limit, this effectively becomes some kind of a continuum, and this is ADS2. So you can get here the boundary, which is just the quantum mechanics boundary. That's where I put all of these insertions 1 minus beta h over L. But there's also a geometrical picture where this dense grid of chords just becomes the bulk of ADS2. Okay, so I can get here.
So how do you see it's ADS2 as opposed to any other two-dimensional geometry where you're saying it becomes dense, it doesn't say it's hypermodal.
Okay, so I want to substantiate this a little bit. Okay. I mean, there is a, well, okay, let me substantiate this.
In what sense do you mean that it becomes this, like the picture it draws, or?
So this is a claim which is, okay, let me substantiate this. And so there's going to be, at this point, there's some flimsy evidence. And I'm going to settle for this flimsy evidence. Okay.
What, do you have other diagrams, or these are the only diagrams that are available?
The chord diagrams are all the diagrams that you need to include in this limit for a single trace object.
So you have everything.
I have everything,
And
yes.
it's not that this is what you have, and it better do it.
This is what I have, and it better do it, and I think it does it. Okay. Okay, so in order to probe this, I mean, of course, you see, ADS2 is a rigid space. Okay, so there's only so much that you can expect to a rigid space to reproduce somehow. But let me, I mean, it's not that I really see like fluctuations and I can measure curvature, etc., etc. But let me go a little bit in this direction. Okay. So what I want to explain is what are the probes. Like, you know, if I really want to.
I mean, are you saying? I'm not sure what you mean by saying. You haven't explained what you mean by a continuous surface emerging.
Mm-hmm.
This should look like Escher.
Why like Escher?
Well,
What do you mean by Escher?
Escher.
Expand
Escher has a visualization of I should say, for example, so during those intersections you have a lot of triangles. We thought of as a
Right.
triangulation.
Some dynamical
So it should
triangularization.
look like Escher. And remember, and I
So let me jump ahead, not quite what I was planning, but let me jump ahead. This is a preview, a little bit. Okay, so we had, well, let me do it systematically. Well, okay, let me not do it systematically. Okay, so let's go back to this picture of the linear code diagram where I start at 0 and end in 0. So, you know, I have, something like this. I don't know, something like this. And then I'm taking this to be, I'm taking more and more points. Okay, because, so basically, at the end of the day, what I'm going to have, I'm going to start at 0 and end at 0. And I'm going to have some profile of the code number. Okay, so here I can parameterize this by n as a function of some discrete time, which is the number of codes open. So this corresponds to n equals 3. Okay, fine. So now I tell you that I go to finer and finer points here, and I have many more codes. Okay, so this n starts to look something like this. Okay, so this is going to be, I'm going to call this the envelope of the code diagram. And basically, I'm summing over all codes, all code diagrams with this envelope. Okay? Now, what I'm going to argue is that if you think about the motion of the boundary particle, this line corresponds, okay, so I need to tell you what's the boundary, there's a boundary particle and it does some motion. I'm going to start and end its motion with this, what becomes the Poincaré horizon. Okay, so this is the disk. And if I want to work in Poincaré coordinates, there's a special point, which if I go to the Minkowski version becomes the Poincaré horizon. Okay, so this is the h squared over h squared plus dz squared over h squared. And here this is h going to 0, and this is h going to infinity, just this specific point. Okay. Now, what I'm going to explain, I hope to get to this, is that this line corresponds to the boundary, to the motion of the boundary particle. This guy, all of these points are mapped to this Poincaré horizon. And this piece of the diagram is this piece of space-time, of ADS2. Okay, the goal for the rest of it is to substantiate this picture. Okay, but in this sense, I'm reproducing the dynamics of ADS2. Good. So, if I want to substantiate anything like this, I need to give you some additional probes. Okay. So what are my observables? I want to start putting in particles in my bulk. Okay. So suppose, okay, so what's going to be my model for particles? It's going to be the following. I need to give you operators in the field theory, right? Because particles in the bulk correspond to operators in the field theory. So I'm going to take something which is very similar to the Hamiltonian with one slight variation. So I'm going to sum over index sets I prime that have length P prime, which is different from P0, which is the length of the Hamiltonian. And then have some new coefficients, which I'll call ji prime for this operator, and then monomials that have to do with this index set. Okay? Now, and these are Gaussians. And there is some normalization here that I have as before. Now, why is this a good model for an operator? Because you really, one way to think about this ADS2 is as the near horizon of some higher dimensional black hole. So this would be some ADS2, say maybe cos S2 sitting inside some ADS4. Okay. And really your observables are determined by what are single trace operators that you can put on the boundary here. Okay. So one of the single trace operators that you put here is a local insertion of the energy momentum tensor that flows to the Hamiltonian. But this is just one operator that sits in a single trace, in some family of single trace operators. You can take any other single trace operator. But you kind of expect that it's going to be of a kind of similar statistical class as the original Hamiltonian. So I want to take operators which are similar to the Hamiltonian, but I want to allow to have different masses, right? I just don't want to only have operators of dimension 1 like the Hamiltonian, and therefore I allow this length to be different. So if I think about, the limit where this is an ADS2 and this is supposed to give me some mass, what's going to be the dimension of this operator in the infrared? Suppose this length is P prime and not P0. If in doubt, guess. That's always a good start. What? Almost. Right, so if I start with something which is of length P0, this gives me the Hamiltonian in the infrared, whose dimension is 1. Right? It's a conformal theory, almost nearly conformal, and the dimension is 1. So this guy is P prime over P0. Okay, this is going to be the dimension of the operator. So by tuning this length to be whatever I want, I can get a particle with whatever mass that I'm interested in. And I think about that as really some object that I had to tell you in advance. It's some information that's missing in the theory and I need to add it. So let's see how we probe this guy. So let's go back to this picture. And suppose I want to compute a two-point function. Okay, something like this. Okay, and I have these insertions of h's. What will change in this diagram because I've inserted this additional operator O? I mean, what's going to happen is that I'm going to have two places where I've inserted O, right? So there's going to be an O here and an O here. Right, this guy is e to the minus beta h, e to the minus ITHO, e to the IT1H, e to the minus IT2HO, e to the IT2H, trace, average. And then I expand each of these guys into a monomial of h's. So I'm going to have lots of insertions of h's in all of these lines. and then there's going to be an insertion of O in two places. Okay, I repeat the same game that I had before. And what I'm going to have is I'm going to have a line like this. And then I'm going to dress it with all the H codes. Okay, and this is the kind of diagram that I'm going to have to compute. Now, what are the rules for this diagram? The rules for this diagram are the following. I still sum over all the chord diagrams. There's now one additional chord. For every intersection like this, I put a Q, which is what I had before. For every intersection like this, I put a Q tilde, where Q tilde is e to the minus p prime p0 over n. Okay, let me remind you that Q was e to the minus p0 squared over n. Okay, so I can compute this. You can pretty much compute this. And let's process this a little bit. This is the two-point function. So the two-point function really, you know, what do I expect from gravity? You know, suppose I had an expression like this. I'm sorry, this is the propagator of some particle. And suppose this was a geodesic of length L. Okay, suppose there was some geodesic between them with renormalized length L. Remember that I always need to renormalize things when I go to the boundary. Then this guy would be e to the minus m, the mass of the object times L. Okay, and in the limit where the mass is large, and I don't need to worry about these small shifts that sit inside the square root, this is going to be e to the minus delta times L, where L is measured in the ADS radius size. On the other hand, this is, okay, so this is the same as e to the minus p prime over p0 times L, again with L measured in the ADS radius. And how is this related to the chord diagram picture? This is this Q tilde to the number of intersections. And let me be a little bit imprecise. I mean, I need to sum over many chord diagrams, so this is Q tilde to some average number of intersections. So let's plug in the formula for Q tilde. Right, so this is, let's continue, this is in the chord size, so this is e to the minus p prime p0 over n times, let's call this k. K. Okay. So what I'm going to get is that I can think about this line. I mean, like, the formulas that you're going to get are okay. If you think about this line starting from here to here as a geodesic, and its length is a p0 squared over n times k, which is this lambda times k that I told you before. Okay, you see, really the only information, I mean, like the non-trivial test here is that this p prime disappears. So any mass that I put will register the same renormalized length of this geodesic. Okay, so that means that for all practical purposes, I can think about a line going from one point in the chord diagram to another point at the edge of these chord diagrams as a geodesic, whose length is proportional to the number of other chords that it intersects, with this coefficient lambda. Okay, now ordinary, so I have here some story that in this chord diagram in general, lengths in space-time are discretely quantized. And if you ask, does that agree with our ordinary gravity? Let me remind you again these formulas that Q is e to the minus lambda. Gravity is when Q goes to 1, so lambda goes to 0. So what I have is a bunch of discrete, all geodesics are of discrete length. And there's a very small coefficient in the gravity limit of just how discrete they are. So if you wish, this lambda is, again, this is the more speculative part, is like a quantum gravity size, where lambda times the ADS radius is some shortest distance that you have in the theory. So in this code diagram, when I have all of these things, distances between 2 points are measured by how many lines do you cross. Okay, so that's the thing that replaces geometry. And in fact, so let's go back to this picture and try and measure distances in this diagram. Okay? So I'm going to kind of improvise now. Okay, suppose I want to, I try to argue that I have this motion over here of the boundary particle. So this line is this line. Okay? And all of these guys are this point. Okay? So suppose I want to measure the distance from here to here along some geodesic, and this is a point at some time t. Okay? The way that I can measure it, I can just, ask what's the envelope here? Right? Because this envelope here is the number of chords that cross this line. It's going to correspond to the length of this object. And therefore, what I'm going to have, I'm going just to have the length of this guy. Okay? Now you can, I'll have some time to do it. You can basically go through all of this reduction that Ahmed did and show that this is exactly what it gives you. That the length here, the envelope of the chord diagram is just measuring length that you have over here. Okay? So I didn't give, I just basically gave you I kind of gave you one conjecture at the time, and I said, if this is true, what would be the implication of this? But there are some consistency checks that you can do. Okay. So, so I have some more time, so I'm going to do this a little bit more systematically. Okay, but let's just write what's the, until when do I have?
When did you start? It was not here when you started, so I cannot
10 minutes to 2?
Okay, so an hour and a half almost.
Okay. Okay, so let's just make a list of the stuff that I've argued so far, and let's try and make it a little bit more rigorous. Any questions so far? Okay, so we had these chord diagrams. The length here, and a chord like this, we want to interpret as a geodesic. Its length is discrete. So L equals lambda times the number of chords that intersected. And I want to make this a little bit more substantial. But let me first give an argument why length, this is a Euclidean picture, by the way, this is just the Euclidean there. So let me give you another argument why space-time is discrete. And that's a very simple argument. Suppose I give you, let's look at this envelope, okay? It has some E min and E max. So there's a finite range of energies, okay? So suppose I have a system with a finite range of energies. That basically means that it's defined on some discrete lattice. Now, if I had some theory defined strictly in the continuum, I could go to shorter and shorter distances, and I would expect energy to go higher and higher. Just the fact that I have here some some finite range of energies means that I'm going to have some UV cutoff on all my quantities, which is going to give me some discrete version of space-time. So that's kind of consistent with this picture, although this is a...
It says there's an Emax.
I mean, there's an Emax relative to this. All right, so if I fix this as my zero, for example, then there's a maximum energy that you can excite in your system.
Micha, are you saying that somehow it's inherent in an ADS-CFT that the space be discrete, or is this particular for this case?
Okay, all I'm saying that in this model, if I try and force a gravitational dual on the entire energy range and the entire code description, then it becomes discrete.
Okay, so then it doesn't generalize in any way to just to having ADS-CFT?
Well, I mean, that remains to be seen. Again, I mean, the way I approach this is I don't expect that the details are going to be exactly the same, but this is a working model of a discretization of space-time that has a good infrared limit in the form of JT gravity, and you might as well explore it because there aren't that many discretizations of space-time that give you a good gravitational infrared theory. I mean, like, you know, whether it works or doesn't work, I don't know, but it's amusing, at least. Okay. Question? Yes?
If you go into one limit, this energy range goes to infinity.
Yeah. But you see, the point is that, right, so really there's a minimal length which is lambda times the ADS radius. Okay, and you don't want to take this strictly to zero. You want to work when it's very, very small and see how you deviate a little bit from gravity. Okay. Okay, so let's make this a little bit more detailed. Okay. And I'm going to repeat a little bit the discussion that I had before. Well, let's put it this way. If I gave you the full SYK model and I asked you in the double scaling limit, and I told you to, and I asked you, you know, what's the gravitational dual of that thing, that has all of this structure. So if you believe that any dual to any quantum mechanics should be treated as a good gravitational dual, this is a good gravitational dual. Whether it's our gravity or whether it's the n=4 gravity also, say ADS5, it's a different question. But this is a gravitational dual of a specific quantum mechanics. Okay, so I want to kind of just substantiate this specific picture a little bit with some formulas. So let me remind you the picture of ADS2 again. There are different descriptions. One of them is that you start with the Schwarzian. Okay. Okay, and then you do whatever you want to do with the Schwarzian. But one of the things that people like to do, I mean, this was discussed by Mertens, Turiacin, Verlinde, Hassan Bagratz Kamenev, Maldacena has similar Kitayev. So I'm there's a lot of work of very smart people on this. So I'm just going to quote this in hope that you remember this from Ahmed's talk. You can get this action by starting with an action like this, and what you're going to do here, to go from here to here, you integrate out phi. Okay, and you're going to have just something that is with f. Now, what's this guy? This has two coordinates, phi and f, and what it basically describes is the motion of, what it describes is the motion of some particle on this two-dimensional space, parameterized by phi and f, and these phi and f are actually coordinates of this disk that I told you before. So how do these phi and f sit? So again, I look at this special boundary point, and these are lines of fixed f. Okay. This is my kind of like some Euclidean time slicing of my space. And lines of fixed phi, I'm sorry, this is lines of fixed f, yes? And lines of fixed phi are something like this. Okay. Okay, this is some kinematics of Euclidean ADS2. So this is fixed phi slices. Okay. So you can take this guy, integrate out something, and you're going to get the Schwarzian action. Or you can do something else. You can take this and integrate out integrate out f. And you see pi f this is f dot. Yeah, this is f dot. Pi f is a constant of motion, so I'm going to set pi f equals mu. Okay. And when you do that, what you're going to get is the Liouville action. E to the minus 1. This is what Ahmed did, right? Or told me he was going to do. So I'm going to assume this. Okay, so what does that? Okay, so how do I use this Liouville business? So really this thing, this motion here describes the boundary particle. So, okay, let's stick with the black. So I have this guy, and I have some motion of a particle. And this is my boundary particle, and this is the piece of space-time that I keep. Okay, so the theory is really a theory either of these boundary particles or of sub-regions of ADS2, and I sum over them with some weight. But recall, but there is one subtlety here, which is that the partition function of SYK, so e to the minus beta h, trace average, is not a partition function over all of these trajectories of the particle because there's an SL2R gauge transformation. Okay? So the way that I fix this gauge transformation, I fix some initial and final point, and I don't integrate over it. I mean, because they're all gauge equivalent. So really, this thing is given by the so the partition function is given by the propagator. Okay, and I need to choose a point x if I want to evaluate this. So, okay, this is from the, I mean, this formula is taken from the Kitaev-Su paper. So in particular, all points x are equivalent because it's a homogeneous space. So I'm going to take x to this point. Okay. So I can write the SYK partition function as these kinds of trajectories that I promised you before. Okay? Now, these lines are lines of fixed f. So the distance from here to here is given by the phi coordinate. So as I propagate time along this curve, really my degree of freedom is what's the distance from here to here. So I'm going to have in this picture some quantum mechanics of some degree of freedom, which is phi. And this is exactly the thing that is described by this Liouville degree of freedom. Okay? There is one subtlety, which is what do I do with this x over here? So this guy corresponds to phi going to minus infinity. Again, in order to do that, you need to see exactly how phi and f sit in this, and whether this is phi equals plus infinity or minus infinity, phi equals minus infinity. So these trajectories and the information that it's a Liouville quantum mechanics tells me that the path integral
U is positive, so this is very repulsive, in the region where it's very repulsive.
Right, exactly. So the Liouville wall looks something like this. And the trajectories that I have are trajectories that start way under the Liouville wall. They kind of go out, and then, you know, this guy repels them out. However, they have to reverse at some point, because both at t, at early time, and at late time, t going to plus minus infinity, I have to return to phi equals minus infinity. So the procedure is, I do a path integral, the partition function is a path integral over all of these phi e to the minus L Liouville, action Liouville, with boundary condition that when t goes to plus minus infinity, I'm under the Liouville wall. Okay. Now, here I can also draw the same envelope that I had before. Now, at this level, this is all, this is all GR, right? I mean, I'm not saying anything new. This I'm just copying from Verlinde, Maldacena, Turiachi, Altland, and company. But this is basically the same picture that I had before, except in the continuum, that I can think about something like phi or e to the minus phi as my coordinate, and I start under the Liouville wall. I end under the Liouville wall. And I have some profile of phi as a function of t. And phi just measures distances, or they are related to phi in some simple geometric way. So this guy just goes over to the picture that I had before with the chord angle. Okay. Now, in order to see that, I need to do the reduction from the transfer matrix to Liouville a little bit more carefully. So the picture, if you want to draw kind of a logic diagram, the picture is the following. You have the boundary particle, which equals, which on this Poincaré disk is given by Liouville plus some boundary conditions. Okay. Now here I have the transfer matrix, and I know that this goes over to Liouville. Here I'm going to have some discrete variable n. Okay. And and the relation here, more precisely, is e to the minus phi. Here is q to the n. And let's check what this means exactly when phi goes to infinity. So that means I'm going in this direction. This is phi equals minus infinity. This is phi equals infinity. When phi goes to infinity, this goes down. That means that n goes to infinity. I am way down my matrix. And the length here is large, right? Because the length here is n times lambda times the ADS radius. So this, so phi going to infinity is large motions over here. And phi going to minus infinity, this guy becomes as large as it can. And this guy, the point as large as it can, basically is just n equals 0. Okay, right, because my matrix was one-sided. So what you have here is that even on this side, there is some shortest distance to this special point over here, and that's where you cut off your space. Okay. So this guy is, if you wish, a Q deformation of this model. When you go down the matrix, you restore very large motion of this trajectory, the semi-classical motion, when the boundary particle is very, very close to the boundary. And when n goes to 0, or you reach this special point, you start seeing that there's some discretization of your space, basically. Now the question is, what is this guy? Right, so this guy sits over this guy. Distances, basically there is some notion of distance here which goes over to the notion of distance here in the semi-classical limit. And what you want to know is what sits over here. What's the notion of this discrete space on which you have this Q-deformed Liouville action, the transfer matrix.
Where did you write all that question mark?
Here? Poincaré disk. Okay. So this is this. So this is, and this should be. Okay. So in the last 2 minutes, I'm going to tell you what this object is. Okay? Well, I'm not going to tell you exactly what it is, but I'm going to give you some hints. So basically, I need to find some lattice version of ADS2. I mean, it would be nice to have a lattice version of ADS2. And let me also add one piece of information. Right, the boundary particle is a motion of some particle on an ADS2. It's not a standard ADS2, there is some magnetic field, blah, blah, blah. But basically, I'm computing a propagator like this. So this is the action of the boundary particle. X. Okay. Now this is a homogeneous space. SL2R acts on it. So this H is some Casimir of SL2. Okay. So all of it's basically right. So quantum mechanically, this is going to be some Laplacian. Laplacian on a homogeneous space is going to be some Casimir of the representation. I split the I split all functions. I go into representation of SL2, and this is going to be the Casimir of that of the representations. So what I want to have is some Casimir that produces this finite energy spectrum that I had before, and somehow captures this discretization of my space. So what happens, and I think I'm going to finish with that, is that this SL2 is deformed into an SLQ to the 1/2 algebra. The symmetry of the problem is no longer SL2, but a Q-deformed SL2. And this Q-deformed SL2 is the following. Right, so if you remember, SL2 has L plus minus 1 and L0. That's the standard notation, and you're familiar with the commutation relations. So this guy, I'm going to denote this by B and C. That's the standard notation that people use in non-commutative geometry. And this is replaced by a new object A. And the commutation relations that define this guy are the following. Right, so this is my new algebra of symmetries. B and C are pretty much the same as L plus minus 1. A, roughly to leading order, is something like Q to the L0. So this is your new algebra of symmetries. You can do an explicit computation that shows this basically from 4-point function, never mind. But there's an explicit computation that does that. And then the trick is, can I find some discrete space that realizes this? And I should say that there are two ways of doing it. One, you can either think about a discrete space, or you can think about a space that is a non-commutative space, or some non-commutative geometry. So I'm going to put, what used to be my phi and z coordinates on my space are now not just numbers, but they have some non-trivial commutation relation between them. You can either work in this model or in this model. They are mathematically equivalent in some cases, and you can kind of realize basically what I said before, that there's a Casimir, this algebra SLQ to the 1/2 has a Casimir. You can build some set of representation of SLQ to the 1/2 which describe a particle moving on this discrete space or non-commutative space. And basically, all of these formulas, this guy, for example, has a non-commutative geometry analog. And if you ask, what's the dynamics of this two-dimensional non-commutative analog, you exactly get the transfer matrix that I advertised before. Okay. Okay, but that I will not be able to show in 2 minutes, or minus 2 minutes. Okay, thank you.
If you go to Q equals 0 in this Q-deformed business, do you get ordinary disk? Because from core diagram point of view, you just get the disk for random matrix theory.
Yeah, but then it's only non-intersecting cores.
Yeah, but I'm not considering homogeneous.
Well, I mean, You're asking what happens to this construction in the limit q going to 0?
Yeah, it's ordinary.
I don't know exactly how you treat this when q going to 0, but this is not what, in the sense of tooth, you would call the disk. I mean, in order to really build like a real two-dimensional surfaces, you need all of these higher order interactions that will introduce vertices in the interior, and you need to double scale that in some specific way. So just the Gaussian GUE ensemble doesn't really have a disk space-time interpretation. So just the q going to 0 limit by itself, you may be able to squeeze something out of it, but it's not what we call 2D gravity in the sense of getting it from a tooth thing.
Is the value of Q which give you the ordinary SL2?
If you take q to 1, this becomes an ordinary SL2. Because when you take q to 1, you really need to look at the generator a minus 1, and then maybe with some power of q, and then these guys go over to the SL2 generator. So this is like a group element, and the b, because it's something to raise to the power of a generator. So this is a group-like element, and these are algebra-like elements in the quantum group.